Welcome to the final episode of The State of Our Blue Machine. And in this episode, we're going to be talking about the Voyagers, because our ocean has a huge variety of habitats, and of course the ocean connects the land together. And there are those of us who are not happy with just being carried along in life. We want to go our own way, we want to choose where we go. And so the Voyagers are those of us who swim or sail or whatever it is to get through or across the blue machine to somewhere else, either somewhere in the ocean or somewhere on land. And of course that can mean migrating blue whales, it can mean fish that migrate to follow the food, or it can mean humans crossing the ocean to trade. All of us are voyagers. And so the first thing we're going to be looking at is actually an obstacle to voyaging, because that is a hurricane. Especially in the near tropical regions of the ocean, you get these huge rotating storms. And if you're a voyager, they really are not what you want to be finding in your way. So let's talk to the people who are trying to predict them and to see what's happening about them in the future.
We provide free climate risk assessments for low-income or historically marginalised communities on a non-profit basis, from fire, temperature, drought, and physical oceanography as well, which is why I'm here.
So give me an sort of specific example, perhaps an ocean one, of one risk and who you tell about it and what they can do with that information.
Okay, yeah. So I guess one of the things we're presenting here at this conference is a new framework we've been developing for trying to estimate the storm surges due to tropical cyclones. So the high winds and the low atmospheric pressure in these obviously very powerful storms can raise coastal sea level by several meters. And
the problem is that it then comes inland, right? So that's what people associate with storm surges. It's not just that you've got big waves breaking on the beach. It's that the water level is actually higher and it's being pushed onto land, and then it's pushed further inland. It can do a huge amount of damage.
Yeah, exactly. Yeah, so inundates huge swathes of land, can destroy coastal communities. Probably one of the most destructive climate hazards when in like single events. So the framework that we have is working to estimate that in the present, estimate the risk of that in the present and in the future as well. And we provide these high fidelity kind of maps of where the ocean could actually extend to inland to help inform coastal communities.
And so for example, if you were, I don't know, you owned a business in that near the coast, or you were about to buy a house, for example, or you were just a city planner and you had to work out where you were going to allow buildings and where your roads were going to be. This is the sort of information you need, because the way these things were in the last 20 years is not going to be the way they are in the next 20 years. Is that right?
Exactly, yeah. So I guess we've got sea level rise is just sea level rise alone. Even if the storm surge itself doesn't change, it's going to increase the extent to which that flooding can happen. And then the hurricanes themselves are quite possibly changing going into the future. The intensities of these storms in some areas could be getting more powerful. The actual locations of these storms as well could be shifting going into the future. So projecting that forward, as you say, is very important to help communities to plan ocean defences, seawalls as well, that kind of thing. Yeah.
And so tell me a little bit about the communities that you are providing this information to. Why is it that they don't have access to this information, and how do they use it once you give it to them?
Yeah, so often a lot of this information is trapped behind barriers like paywalls. I guess in the centre we really believe that all of this data should be completely open access, open source. All of our methods are open access.
So just to clarify what that means, because I think that's kind of one of those science terms that everyone else doesn't necessarily. It means that if you produce something, or actually if I produce something as a university scientist, whatever report or paper or tool, it is then put on a web page where anyone can get to it. So there's no gateways, there's no fees need to be paid, there's no barriers.
Exactly.
If you need it, you can go and get it, and that's what open access means.
Yeah, exactly. And we really are working towards making all of our data and our methods open access, so that communities which historically may not have the resources or even the expertise to do these kind of climate risk assessments are able to access that without having to pay. Because many of these communities are also some of the communities that are most at risk from the perils faced by climate change.
So this is one of the biggest sort of ethical issues here, isn't it? Is that the poorest communities are often in the land that was a bit vulnerable anyway, and then when you increase the level of risk, they're now very vulnerable.
Yeah.
And they're still there, and they can't just sort of wander off, and go and live somewhere else. So they're kind of stuck. Talk to me a little bit about the sort of, we hear this phrase climate justice a lot. Talk to me a little bit about what climate justice is and how it applies to the work you do.
Many of the poorest communities are there because of the risks that are already posed, and again, in many of those areas, going forward, that's going to become more and more extreme for those communities. And often, these are not the communities which have emitted the carbon, which is actually going to, down the road, is the one that's going to disrupt their life. So climate justice is about, for us, it's about providing these risk assessments, as I say, non-profit and free, so that they can build resilience to these hazards and to these risks.
And just tell us, you've got a poster here in the poster hall over there. Just tell us a little bit about what's on that poster.
Yeah, okay. So the poster is, it's about that new framework that we're developing that uses ocean simulations, statistical hurricanes we essentially do thousands of years of ocean simulation with thousands of years of statistical hurricanes, which allows us to get an accurate representation of how big the storm surge can realistically get for anywhere in the world, in the past, in the present, and in the future. And then, as we talked about, we can take that from coastal heights of the sea level to actually estimating how far inland that sea level can cause flooding on a very high resolution. So we can go down to maybe 10 meters, which allows us to get it kind of to the building scale. We can see which areas of towns and cities could actually be flooded in the future.
So we should probably say a little bit about what a climate model is, or how these models work. And they're basically flight simulators, right? It's a flight simulator for a planet. And if you can have a local model that does one local area really, really well. It's a good flight simulator for that. Or you can have ones that capture the whole globe, but then everything's a bit fuzzier because it's just enormous. Yeah. So you're working with these sort of simulations, and you can run them, you can kind of tweak the weather and tweak things a bit, and then just basically run reality lots of times and see what happens. Is that right?
Exactly. That's a nice way to put it. So we're on the local side of things, I guess, for our framework. So we are able to do these high fidelity, maybe the highly bespoke kind of simulations for a community that we're working with, which allows us to, for example, sometimes if they can provide us with information on coastal defences or very specific local information, we can incorporate that into the model as well to really give them custom bespoke assessments.
Next, we are going to meet some actual voyagers. These are scientists that go out on ships in order to understand the physics and chemistry of the ocean and how it's changing. And the name of their project is Ghost Ship, and I can never remember what that stands for, so I think it'll be written down here. Hate these acronyms. Anyway, this is what they had to say about how the ocean is changing.
It's a program that actually, it has its beginnings way, way, way back in the 1950s. But in the 1980s, there were plans for this program called the World Ocean Circulation Experiment, which began in 1992. It was a massive international effort where they basically crisscrossed the entire global ocean, excluding the Arctic, to just get a single, what they called synoptic survey of the ocean.
So that's a snapshot of the whole ocean.
A snapshot of the whole ocean, and that snapshot took 10 years to make. And that was still back in the day where we thought that the deep ocean didn't change, that the deep ocean was sluggish and didn't move around very much. We got to the end of that in 1998 and realized, but in fact the ocean's changing, climate is changing, the ocean is changing, the atmosphere is warming, the ocean is going to warm, and things are changing. And the thing that distinguishes Ghost Ship from other observation programs is that we do these, what we call sections, that go from land to land on a ship, from surface to bottom when we stop and take measurements. And it's high resolution surface to bottom, and it's high resolution as we go across. So approximately what we're shooting for is approximately every 50 kilometers, we are stopping the ship and we are taking measurements surface to bottom. You can see the structure of the temperature field. So you can imagine that the ocean tends to be warmer at the surface. And if you paint those colors where warm is red and blue is cold, you'll get blue in the deep and red at the top. But there's structure within that. It's not just going from warm to cold. And depending on where you are in the world, sometimes warmer waters go deeper and very cold waters come to the surface because, particularly near the poles, we have what we call water formation. So whenever water is at the surface of the ocean, it gathers its characteristics, its temperature, its salinity, and other characteristics.
So the inside of the ocean has shape.
It has shape and structure, and then we decided we had to keep going because things were changing and we wanted a longer record. You compare one thing to another thing, you can tell that things are different, but you can't tell that there's a trend. The only way we can determine a trend is if we can get more observations, and even 30 years isn't really enough. In fact, we were talking about that at this workshop, about how we can contribute more, how we can make sure that we're doing things in the same way. Because one of the things we really want is high quality. We want the best that we can do.
Well, if you're putting all of that effort in, you want good stuff out.
You want good stuff out at the end, yes.
Okay, so we've got the picture then, you know, that these systems can measure what's happening inside the ocean. And you're talking about the physical and chemical structure, and you can see these patterns. And so, Adam, how do those patterns influence life?
Well, so for a long time, we didn't really know that. We didn't really have any observations. We had theories, but not observations. And so that's how I got involved with Ghost Ship, was to understand not only what was the variability in biodiversity in the ocean, but also you were alluding to the differences in the distribution of phosphate versus nitrate, which to a large extent is biologically driven. So there's also this feedback from the organisms living in the ocean making an imprint on the hydrography.
So it's not just that there's physical processes that mean there's more of one nutrient here, it's that the life itself is helping to move those around and develop the patterns.
Yes. If there was no life, then they would be completely identical. But with the life, that's when they start to split. And so we want to understand the impact of a changing ocean on marine life, and then also in reverse, when marine life is changing, what will that do to the hydrography of the ocean?
So give us an example of one species or a phytoplankton, perhaps maybe something like a zooplankton or maybe something bigger. Give us an example of a type of life and how it might be affected by something in the ocean changing.
Well, so there I would highlight my favorite bug, which is
we're all for people's favorite bugs.
Yeah,
Prochlorococcus. Okay, small one, very small one.
It's the smallest photosynthetic plankton in the ocean, but it's also the most abundant one. And it's found in probably 2/3 of the ocean. And it's incredibly active. It grows very fast, so it draws down a lot of CO2 from the atmosphere and produces food for everyone else. And Prochlorococcus is one of those organisms that really likes it hot. And so the warmer it gets, it's gonna thrive. Unfortunately for a lot of other organisms, that's not the same. They're gonna do much worse. And so some organisms, like my favorite bug, Prochlorococcus, will be a winner, and then there's gonna be lots of losers.
So I remember actually the first research cruise I ever went on was in the Pacific, and the optical oceanographer Dr Stransky was there, and I didn't know anything about the ocean, and we were in completely clear blue. There was almost nothing living there, right? That's when the ocean's bright blue and it's got nothing living in it. And he was there. He'd fished out a sample, and he showed me Prochlorococcus, and he made sure that I knew that this was there, and that even though it looked like there was nothing living there, something was still there. But of course, that's in the middle of the Pacific where it's nice and warm.
Yep.
And so what's the example of a species that might not do so well?
Well, so typically the organisms that really like it on the cooler side, they like a lot of nutrients, like a diatom, they would be the ones that where the habitat, if they're like a polar species, right? Those are the classic ones that where the habitat is going to shrink or maybe completely disappear.
So Adam has just had to rush off to go and prepare to introduce a plenary session, but we are now joined by Letitia Barbaro. Did I get that right? Barbaro, thank you. Who is also connected with the Ghost Ship movement. So we're going to continue the conversation. It's like rotating ocean scientists. It's great. Well, so you missed earlier on. You missed. So Alison described that when you have a sample of water, it's got a character. It's got these lots of different things in it: trace elements, nutrients, and heat, and carbon is one of those things. So just tell us a little bit about how the carbon in the ocean compares with the carbon on the land and in the atmosphere, and why the ocean is important when it comes to carbon.
I think the critical part when we're thinking about global climate and the role that the ocean plays in terms of carbon is that when carbon enters the ocean through air-sea gas exchange, it goes through a series of, let's say, chemical equilibriums that act as a buffer and that allow the ocean to absorb a lot of carbon. And then that carbon, is gonna stay in a number of chemical forms without going into the details, but it's gonna stay there for a long time. And it's playing a huge role in helping us combat all the carbon emissions. The ocean absorbs about a quarter to a third of our human emissions, so it's really helping us delay the impacts of climate change. At the same time, all this carbon that is entering the ocean is altering the pH of the water. It's making it a little more acidic, and this has impacts on the organisms that live there. Organisms that have calcareous shells, depending on the pH, they can struggle to build healthy shells. This, at the same time, in coastal areas, can have significant impact on the communities that rely on all these, seafood and shell organisms. So it's important to monitor it because we want to know how much carbon the ocean is storing, how that storage is changing over time, but also how all this extra carbon is impacting the chemistry of the water and the organisms that live in that water.
To people who don't think about the ocean, it's kind of, I think they see it as the kind of the blue filler between where all the land is, and it's got fish in it.
Yeah.
but it's mostly just it's just kind of the coloured in blue, and we don't think about it. And this drives me nuts, right? I spend a lot of time trying to talk about all of these things. But if you have, if you meet someone at I don't know, a gathering or a party, or you're maybe a school, you're out and about, and someone says, well, all you ocean scientists, you're off doing your thing, but why should I care about the ocean? I've got my life on land, I don't see the ocean, I can do what I do, and I don't really care. Why should I care? Why should people care about the ocean? What do you say?
You should care about the ocean because it is changing, because as your atmosphere is warming and we're beginning to get really annoyed at those really hot periods of time and the rain that we're getting in some places and the flooding and the hurricanes and etc. All those things that are happening where we can feel them at the same time. That warming is warming the waters that are going down deep in the ocean. The ocean itself is warming, and as the ocean warms, it can change its circulation, it can change how much carbon it can take up, it can affect all the animals that are in the ocean. And it's not, we used to think that if you put something in the ocean, you'd never see it again. And it's just not true.
What do you say?
I say, well, it depends on who I'm talking to.
Yeah.
But I try to take it to a more personal level, something that maybe they can relate to. So it could be, and because I work in ocean acidification and carbon chemistry, I tend to take it to that area, which is my area of expertise. And I say, how do you like when you go on vacation to go visit coral reefs? The coral reefs are being seriously impacted today. We're seeing massive coral die-offs in Florida because of extreme heat. We're seeing, fisheries collapse in Alaska because of
There's your salmon.
Exactly. How do you like your salmon? How do you like your lobster? How do you like your shrimp? So the ocean is not this massive thing. You benefit from the ocean on your daily life, even if you don't think about it. There's huge industries, your fellow citizens that depend on healthy oceans. So we need to monitor it. We need to see what's going on so that we can maybe adapt, mitigate, and to the degree that we can, decrease the impact, the deleterious impact that we're having on our oceans. And when you relate to things that they care about, it's easier for them to care about the oceans.
I was in a classroom with young children, and I was telling them about how it felt the first time that I got Antarctic bottom water coming out of the bottle that we'd collected it in and pouring over my hands, and realizing that I was holding water that hadn't seen the surface for hundreds of years.
So the situation we're talking about is that when you go out on a ship, you lower down all these bottles and they go down into the deep water, they trap samples, and you bring them back up, and then there's a kind of tap that you can turn.
Exactly. And you're sampling the water, and you get the water on your hands. And I just found this to be it was almost religious, like almost a religious experience to have this really, really old water. Like I could imagine, an archaeologist sort of delving down to the earth and bringing up history, and that's what it felt like. So there was that experience, and then the other experience, which happened a few years later, was being in the South Pacific, again, as Adam was talking about, being miles and miles from land. The only life that we'd actually seen were albatross that were following us across the ocean. But going out at night and seeing the Southern Cross in the sky, and the sky out in the middle of the ocean is just unbelievable for somebody who's never just been out there. But at the same time, in the water, all the plankton is lighting up. So you've got stars up above and stars down below. And if you can have that, why would you ever not do what I do? It's just...
That's brilliant. That's the best, one of the best adverts for being an ocean scientist I've ever heard. In my professional life, I am a voyager because I go to sea on research ships to study breaking waves and bubbles at the ocean surface. And of course, I don't do that by myself. The ocean is a complicated place. You need these big collaborations. And so I went to sea in the Labrador Sea. So at the end of 2023, the Labrador Sea is up here in a really stormy bit of the North Atlantic. If you are in the market for a nice sunny holiday where it's going to be very calm and peaceful, don't go there. Because there were huge, great big waves, really cold weather, thoroughly miserable, scientifically fascinating. And of course, it's not just me doing this on my own. I work with lots of collaborators, and many of them were there with us in New Orleans at the Ocean Sciences meeting. So we sat down to remember what that expedition is like, what it felt like to be voyagers on the sea, and to talk about what it's really like to get that kind of science done. We were at sea for quite a long time, for 5 weeks, and some time has passed, so it's all settled down. So we're here now to discuss it. And with me here are Krista and Leonard and David, who are all on the ship with me. And we're going to hash out what it was really like, with the benefit of hindsight, when we don't all have to be polite to each other, because we're all going to see each other first thing every morning for the next 5 weeks. So the three of you specifically, the thing I want to pick up in first is that we were in a ship in the middle of the sea, this horrible wintry storms, all this nasty weather, and all you three could think about, as far as I could see, was American football. Right? Am I wrong about this?
Okay,
somebody tell me.
Point in the Eagles' trajectory, and I blame him.
Well, actually, it started already before the cruise.
Oh yeah, that's right. You made me watch a
game.
match. Yeah. But there was this thing about the internet vouchers, right? Do you want to explain the saving of the internet vouchers?
Well, so we had Starlink vouchers from Elon Musk, and
From personally given.
he gave us some vouchers, and we decided to use them on football.
But not only, I also spent all of them on Life Aquatic.
Oh yes, because it was decided we had to watch the Life Aquatic one evening. You had to save them up.
It was really rough from the sea. I've never experienced it that rough. I think it was a challenging cruise because it was always with the weather, if we could work, if we could not work. I've never experienced that much. Before it was more often calm sea, and you could really work day in, day out.
You could have a plan.
Yeah, you could really work the plan from A to Z and not shift it around like Kristen.
Because you had the bulk of
You could
that.
also sleep. Sleeping
Yeah.
So just, I mean, because we had these meetings pretty much every day, and you were trying to coordinate. The weather was doing things, the captain was saying things. Just describe that. Like, have you recovered from that?
Kind of. So I think I'm not ready to do that again yet. But so I haven't fully recovered. But I think the difficulty is really the unknown, right? So you make a plan. People sit together for years trying to coordinate their science. Everyone knows what everyone is doing to a certain extent, and then you get there and suddenly it's all different because the storms hit differently, or the situation is more perilous than anticipated. And so what they thought they could do was different than anticipated, and suddenly you're stuck there, having to come up with a different plan all the time.
And I mean, it was kind of the difficulties. This is all part of experimental science, right? None of this is easy. That's why we do it. But there were, the difficulties kind of started quite early. And there's a picture of you that I love, which has. There was a gas bottle, and there's a picture of you hugging the gas bottle before we left the port. Can you just tell us why you were hugging the gas bottle?
Well, so I always say international shipping is the enemy of science. So it's really hard, maybe because we're such amateurs at it. So I was expecting these gases to show up, and they were being held up in Maine, I think. And then nobody tells you about it. And I think we had to delay the cruise by at least a day.
It was one day.
Yeah, for this critical gas to show up.
And how? Because your experiment was kind of stressful in the sense that it sort of didn't stop. You had these invisible gases that you injected into the ocean, and then you were always responsible. How hard is it? Just describe a little bit that experiment. Why it is that you kind of couldn't switch off really.
Well, it's like you said, it's invisible, so we depended on our instrument to measure it, but we often didn't have a good sense of where this tracer patch that we were tracking was going. So sometimes we would lose it, and then we would have to try to find it, and you always have this dread that you would lose it for good. So it was not easy.
I remember someone saying to you, well, how long is it going to take you to find it?
It's hard to schedule finding something you've lost.
Right.
Yeah.
Could each of you identify like a worst or best moment about the cruise, one or the other? You can have a moment to think about it. I'll go first with one of the best, and it was so I had this bubble buoy that was very large and that had never been put in the ocean before. And it floated, which was amazing because I didn't know it was going to float. I genuinely didn't know it was going to float when we shipped it there, and it went out for a couple of hours, and it went out for a few more hours, and then we put it out properly, and then the seas were so huge. There were wind and the waves, and I was terrified this thing was going to sink. And all I had there was a little beacon on top that was sending me emails every half hour, and I was just checking my email because if the beacon was sending signals, then it hadn't sunk yet. And so I spent I think it was 6 days, and there was this massive storm that never seemed to stop, and all I could think about was, is there another email? Has it not sunk? Because if this thing sinks, literally every piece of scientific equipment I own has just gone down with it. And it came back. And I remember when I was on the bridge, and I think it was dark and they were recovering, and there was this little light in the distance, and we can see it, and it must still be floating. And I was like, that relief, I will remember that. So that was one of my favorite moments. Would anyone like to pick a best or a worst moment? Leonard?
A worst moment for me was probably during that one night when it was so rough that you really couldn't sleep.
I remember more than one.
It was one night. It was one night that was sticking out for me at least. And the best moment probably that the cruise actually happened, because we had these difficulties in the beginning where we had discussions if it would really happen now, or if it would be postponed, or if it would just be cancelled. And then actually pretty much when we left the harbor, that it happened.
That's a good point. And just that night, as I remember, because the reason that night was so bad is we'd been in quite quiet water. We went around Newfoundland, and then the wind went from 10 meters a second to 30 meters a second over 12 hours. I think it was really quick. And the thing is that normally when that happens, it gets a bit higher, and so you strap a few things down, and then it gets a bit higher and you strap a few more things down, and that was the ship was rolling so much that everything was moving that night, and it was like you say, I had not appreciated how slippery bed sheets are before. You just slid down one end and then slid back the other way. Okay, best and worst moments, David, or worst, one or the other.
Well, the best moment was probably when the 49ers beat the Eagles.
For some people.
No, I'm kidding.
No, you're actually not.
You're not, are you?
I think you're not.
So, there were those times when the weather was so bad that the ship basically couldn't steer. So we, had to leave the tracer patch for, sometimes more than a day. And then we were able to go back and actually find the tracer patch, which to me was a miracle. And that happened at least twice.
2 miracles for you.
Yeah.
I think it was quite often. It was pretty
more than
impressive.
twice.
But it was twice that we went a really long way when there's just that line, and then we all got up and the ship's all the way over there.
Yeah.
So that was pretty great, I thought.
And Krista, one moment that stands out for you?
I mean, so there were a lot of bad moments. It was I love to go to sea, but there were a lot more bad moments than good ones. So I think, sounds very odd to say, but I think a really good moment was when we actually arrived to St. John's and everyone was safe and all the equipment was on board. We got it all back and it worked. I mean, so I even had some difficult conversations with the crew at the end, and finally we concluded that despite all the difficulties, it was quite successful. And I think for me, this was a very good moment because we survived. And we could all go home with something special. I think the data that we collected was extremely rare and definitely will be useful and special. So we made it.
Yeah, and you're right that we can't take this for granted, right?
No,
I mean, the reason this is hard is that it genuinely might all go wrong. I mean, not necessarily from a safety point of view, but from experiments not working, from all
So
of that,
many
like,
things.
and it is to your enormous credit, because you were doing a lot of the organising, trying to navigate all of this, and you did an enormously diplomatic job of managing all these things. And it, but it takes that, there's a teamwork thing, right? The people are the most important thing on board, and they don't always get on with each other, and they don't always agree, and that's all got to be managed. Brilliant. Well, thank you all very much. While we were in New Orleans, and I was telling producer Trent about this expedition, he said, well, what did you find out? And I said, I don't know. We need about a year after the expedition to just get through the basic data analysis to find out what we really saw. It is now a year later. A year ago today, I was on that ship up there, and I can tell you that we have still not analysed the data because it's long and complicated, and we're still digging into the nuts and bolts of it. So I can't tell you what we found out just yet. I can tell you the data's looking really good and really interesting. I don't have any conclusions just yet. I'm possibly making myself a hostage to fortune here, but I reckon that by the time we get to the Ocean Sciences meeting in Glasgow in February 2026, I should have some results to present. That is the aim. Let's see if it happens. Some of the voyagers of the future are not going to be minerals or animals or humans. They're going to be robots. And we need this really because the ocean is so big that we can't physically send enough people to study it. But we are increasingly building devices that can get out into these remote places, stay there for months and collect the data for us. So next, it's time to meet Sail Drone. Brian, we are here. You are very orange, and this is very orange. Tell us, this is Sail Drone. Tell us what it is.
So this is a Sail Drone uncrewed surface vehicle. This particular one is wind propelled and solar powered. It can stay at sea for up to 12 months. It collects ocean science data, everything from wind speeds and direction, wave heights. We can do fishery surveys. We can do current measurements. The particular one you see here with a kind of a stubby wing, as we call it, it actually was designed to drive into hurricanes. And so we actually drive into the eye wall and measure the air-sea interaction that's happening to try and understand intensification. So we had a big partnership with NOAA here in the U.S. to try and improve their models for intensification of hurricanes. And so We've had 12 of those out last year that got into hurricanes and collected some great data and some good video, which went viral on the web with no one's really seen inside of a hurricane before.
Because you don't go there.
Because there's a reason you don't go there.
Yeah.
Exactly.
As someone who studies storms, like I spend my time researching out on ships in big storms, and I would not go see a hurricane,
Right.
but this can.
This can, that's right.
And how many? So I remember a few years ago when people first started talking about sail drone in the ocean community because it was something different. Just tell me why it's different to what we had before.
So it's different because you have something now that has the ability to stay at sea for a very long time. So this particular drone could actually stay at sea for up to and over 12 months. Normally, if you're going out on a ship to do a study, you have a finite amount of money to pay for that ship time. Buoys stay in one place or they get swept around. So now you've got the ability to drive the vehicle where you want to measure something and do as long as you need to. So if you're trying to do seasonality of data, or you see that maybe the feature you want to look at is 100 miles the other way, you can actually now steer over there. And so it's all enabled by the fact that we're harvesting wind and solar energy to operate these vehicles, and use satellite communications then to drive them where they need to go.
And I tell you, the first thing I think, so I know that when you're on a ship, the thing that you notice is that first of all the birds follow the ship because it's interesting, and if there's anything that is sticking up, they will circle around it and try and land on it. So why do these come back just covered in bird poo?
We have had that issue. We also have got some great pictures of like red-footed boobies with their face in our camera and just kind of looking in. But we do put up on our drones that are out now, we put up some of the little spikes that stick up on so they can't land.
Oh, so no sofa for a bird.
Right. Now we did have a sea lion catch a ride one time.
Oh.
So that's biofouling.
But it pulled itself up on top.
Yeah, it got it right on top. So.
Wow. And it didn't sink.
No, they won't
That's quite
sink.
impressive.
Yeah.
So just looking forward, maybe 10 or 15 years, we're starting to see these in the past, in history, oceanographers had to go on the ship and they had to dangle things over the side on glorified bits of string. Basically, That is how oceanography was done until, maybe 20 years ago, perhaps, right? It's not a long time. But just thinking ahead, perhaps 20 years, just describe to me how you see the ocean being monitored overall. Paint me a picture of all the ways we're going to be looking at the ocean, perhaps including the sail drone.
Yeah, starting in space, we're going to have more satellites that are going to be able to measure more things. A lot of smart people are working on what kind of sensors are out there and can measure from space. Once you get down to the surface, vehicles like this that have this very long endurance, we're going to be more capable. Maybe we'll be able to launch and recover gliders or drop buoys or XPTs and the things that you used to do with ships. Maybe that's where we end up, is that we can actually deploy things, or maybe we can deploy an aerial drone that can go out and look at something specific on the surface. And then I think you're going to see a lot more ocean gliders, and also the AUVs themselves.
So ocean gliders are things that they look a bit like underwater planes, but they do kind of fly underwater, but they can go very long distances.
Very long distances, and then when you have AUVs that are powered, those mission lengths keep getting longer and longer, and the technology of the sonars and the cameras, those are all, all that stuff is just going to get better. And by having more of them, hopefully the cost, the price point will come down, and it will make it easier for more scientists to, study more things. And I think we're already seeing that with vehicles like ours. When you compare what you can do with us to a ship, there's really no comparison. But we can't do everything a ship can do right now. We do have a winch on our bigger vehicles, but it only gets us down 450 meters. It's not a full rosette that you can drop down to 6,000 meters. We're not going to, right now, we're not launching AUVs. We're not stopping and putting an ROV over the side. But if those ships could focus on those exquisite things that only they can do, and let the robots do the other stuff, the data collection, the mapping of the ocean, that's really the sweet spot, I think, in the next 5 to 10 years.
And just finally, tell me the big picture of I'm used to saying that oceanography is data poor, right? Because we scrabble about for every single measurement and it's hard. And suddenly you come along with things like this, there's just numbers everywhere. Right. Too many numbers to deal with. But why is it so important now? Just tell us a little bit about why it's so important now to monitor our ocean in this level of detail.
Well, everybody talks about global climate change, intensification of storms, potential changes to ocean currents. And so you can't monitor or manage what you don't measure. And so we need to be out there measuring and trying to get ahead and see, are the programs that we're trying to reduce carbon, are they working? If they're not, then we'll have to do something different. And so, but if you're not measuring as much as you can, and the ocean's just so huge, and there's so many things that can be going on out there, you have to be persistent. You can't just go over one day and drop a buoy, or an XPT, and that data is just a single point in time. Whereas vehicles like these that stay out for long periods of time, you get that repeated measurement, and you can start to see changes. I think that's why it's really important right now. If we want to affect, or take action against climate change, well, first we have to understand where it is, and stuff we're already doing, is it making a difference or not?
Now, why should we limit ourselves to voyaging through only Earth's ocean? Earth is a wonderful place, but it's only got one big ocean. What about the others? Because there are others out there. We think that on moons out in the solar system, and maybe even on planets further afield, there are other oceans out there in the universe. So we spoke to someone to find out what they might be like.
I study ocean worlds, so I specifically look at ocean worlds such as Europa and Enceladus. Europa is a moon of Jupiter, Enceladus is a moon of Saturn. They're covered in ice, and underneath we're fairly certain that there's liquid water oceans. And I'm interested in how have these oceans formed and changed over time. What is their composition? What are their temperatures? How big are they? And so I look at how these oceans changed over time, basically, and what could they look like at the modern day. If we really want to go all the way back, the first time we ever saw Europa, at the time we didn't think that there was an ocean, but the very first time we saw Europa was actually Galileo Galilei, way back when he invented the telescope, looked up at the stars, and he saw Jupiter, and he saw tiny little pinpricks of light around Jupiter, and he noticed that they were orbiting around Jupiter. And one of those pinpricks of light actually was Europa. So the very first time we observed Europa was actually by Galileo Galilei. And then over time, we've sent different missions throughout the solar system. So we had the Pioneer missions, and those flew by Europa. We saw a little bit of its surface. We saw that it wasn't heavily cratered, which is what we thought it might be. And usually if things aren't heavily cratered, that means that there's something interesting going on. They're geologically active. After that, we had the Voyager missions, and then the Galileo. And the Galileo was the one that actually allowed us to determine if there was an ocean or not. And so Galileo had a magnetometer on board, and that magnetometer allowed us to look at the different fields as we flew by it. And what it showed was that there's potentially is a liquid water, salty liquid water layer within this ocean, or within this planet. And so the Galileo mission was really the very first evidence for that, and that started to become an idea in the late 1990s, but really came to be an idea that there is an ocean here in the early 2000s. We really don't know exactly what the composition is. We do know that it's probably salts. It's probably less salty than our own ocean, but we don't actually know. We have the Europa Clipper mission launching in this October, and that mission will hopefully help us get a better idea of actually how saline is this ocean. Is it, just a little salty, or is it really, really, really salty? We don't know for sure. But if we look at the surface, we can maybe get an idea of what the composition of those salts might be. And on the surface, we've seen sodium chloride salts, we've seen magnesium sulfate. And so these are two different types of salts that might be potentially in the interior that have been, potentially through different geological processes been brought up to the surface. And that's what we're seeing is, evidence of the salts in the interior. But we won't know for sure until we go and take better data. The mission's primary objective is to examine habitability. And so habitability is a slightly different thing from looking for life. It's the first step to looking for life is not only, before you go to and looking for life, you need to understand, can life even exist? And so that's what we look for, that's habitability. And so that's understanding the salinity of the ocean, the composition, the different processes that are occurring. And so this mission will be going and looking at what are the different chemical building blocks that are potentially there, how much water, how big is this ocean? We don't actually know how deep the ocean is, and so we'll get a better idea of that. And what are the circulation patterns, what are the different processes that are going on there. That'll help us get a better understanding of what the habitability of this of Europa is. That would be really, really cool. That would be absolutely inspiring, just because currently as far as we're aware, Earth is the only place that has life. And there's life everywhere on Earth. I mean, everywhere you go, there's microbes, there's fungi, there's people, there's birds and worms. And so there's life everywhere on Earth. And so how is it that, this one place we know of that has life has so much of it, but everywhere else we've gone, we don't really see anything. So what's this understanding, maybe what's this barrier between having no life and having this rich biology, this infested, if you will, planet that is Earth? Is there like a bridge or some sort of gap you have to jump to be able to get from no life to what we have here on Earth? And so if we can find life elsewhere, that would mean that we potentially can understand where that gap lies. And so where that bridge from just, plain, simple molecules to more complex chemistry, complex organics, and eventually, getting into a life form. That would be, knowing the difficult part of that process would be huge.
We are extremely grateful to all the scientists who gave their time to talk to us, to share their science and their enthusiasm at the Ocean Sciences meeting. So a big thank you to all of them. And also thank you to the AGU, the American Geophysical Union, for inviting us along and hosting us during the visit. And if you haven't checked out the other episodes in this series, you definitely should. And the place to look is the Cosmic Shambles YouTube channel. And so that's it. The last episode of this series has come to an end. And thank you for joining us on this journey. If you like what we do at Cosmic Shambles, don't fear, there is plenty more out there. So have a look at cosmicshambles.com. There's other documentaries, there's live events, there's lots of stuff on the go. And do have a look at the links down below here to like and subscribe to the channel. If you'd like to support what we do, please go to patreon.com/cosmicshambles, because that is what helps us keep this freely available for everyone. And that's what we want, to share these ideas as widely as possible. But for now, from the Ocean Sciences meeting in New Orleans, goodbye.
Thank you for watching. I hope you've enjoyed it. Even if you haven't enjoyed it, I still think you should support us at patreon.com/cosmicshambles. And also, by the way, click and subscribe. That's what they say, don't they? I'm 55 and I'm having to say click and subscribe. I mean, just for the loss of dignity, you should click and subscribe.